Hey guys, welcome to the Tutoring Bros, and today's topic is stoichiometry. So what stoichiometry is, it's an aspect of chemistry that involves using relationships between products and reactants in a chemical equation to determine a quantity of a product or a reactant in that same equation. So stoichiometry is vital in chemistry. It is used in high school chemistry, AP chemistry, college level general chemistry. It is used throughout the whole semester or year, and it just gets more advanced or more complicated as you go on. It starts involving density, starts involving molarity, molality, all these things. So you want to have a good grasp of it in the beginning. So stoichiometry, when you're first starting out, involves three main things: moles, mass, formula units. So let's look at moles first. So a mole is representing a quantity, and that quantity is this number. It's a very large number, but because we're dealing with atoms and molecules which are so small and so abundant, we have to use this very large number to describe their quantity. So the same way a dozen means 12, a mole means 6.022 times 10 to the 23. This is a shortened version of it. You can sometimes see 6.02 or more numbers after these two numbers. So it can look different, but generally it's going to look like 6.022 times 10 to the 23. So let's look at mass. So mass is easy, it's grams, kilograms, milligrams. When you're first starting out with stoichiometry, you're generally going to want to focus on grams. Kilograms and milligrams, if you get a quantity in that number, you're going to want to convert it to grams for the most part, for 99% of the time. This is why in stoichiometry it's important to write out your units, because you know when to use grams, kilograms, milligrams, but for the most part you will be using grams. And then formula units is molecules / atoms. So they both mean the same thing in calculating the equation, but it just depends on saying molecules or atoms on what you're dealing with. So if I'm, for example, dealing with the stoichiometry equation of NaCl, I would say molecules. But if I was dealing with just Na, I would say atoms. So what you call the formula units won't affect your calculation, but it will affect if your answer is technically correct or not. So this is something important to watch out for, and just to make sure you have correct terminology. So what is the relationship between all three of these things? So say we have molecule A, okay, and say we know the moles of A, okay. Well, from moles of A, we can convert that moles of A to molecules of A. And since A is a molecule, that's what we're going to call it. That's what we're going to call its formula unit. So we can go from moles of A to molecules of A, molecules of A to moles of A. From moles of A, we can also go to mass of A in grams. Okay, so mass of A to moles of A. Can we go to mass of A directly to molecules of A? No. We have to go to mass of A to moles of A, and then moles of A we can go to molecules of A. So we can't skip the moles, The moles is the intermediary in everything. That's why it is so vital in stoichiometry. So say we have this equation, A plus B. A and B react and they form C. Okay? So say we want to know how many, so say we know how many moles of A we have, and say we want to know, oh, we have this reaction and we want to know, oh, how many moles of C will this amount of moles of A create? So from moles of A, we can go to moles of C because we have this equation. We have the relationship. So looking at this equation, we see 1 mole of A reacts with 1 mole of B to create 1 mole of C. So we have that relationship. Okay, and then it's the same for moles of C. We can go to molecules of C, and we can also go to mass of C in grams. Say, though, we want to know how many, the amount of moles of A, say we want to know how many molecules of C that produces. So what we'll do is, we'll start with moles of A, we'll go to moles of C, then from moles of C, we can now go to molecules of C. So again, the moles is very important. It is important when dealing with just one compound by itself. It's also very important when converting between compounds. It's the only way you can convert between two different things. So now let's look at some practice problems. So say we have this equation. 1 mole of methane reacts with 2 moles of oxygen to create 1 mole of carbon dioxide and 2 moles of water. And then we have this problem. If 0.264 moles of methane is reacted with excess oxygen, so what this excess is telling you is our oxygen is in abundance. We don't have to worry about its amount. It's not going to be a factor in our stoichiometry calculation. So it's reacted with excess oxygen. How many moles of water will be produced? So let's start this. So we start with 0.264 moles CH4. It's always very helpful when starting out to write out your units. Don't just write out the number, write out your units. Okay? So we know we're going to be doing a conversion, and like how when we convert from centimeters to meters, or kilograms to grams, we're going to set up our little conversion equation. Okay? So we're going to multiply our moles by a fraction. So how do we know how to create this fraction? Well, let's look at our chart. Let's say methane is A and H2O is C. So we want to go from moles of A / methane to moles of C / water. Well, look, we can go directly from moles of A to moles of C. So let's do that. So how do we know what's going to go on the bottom, what's going to go on the top? Well, we want our answer in moles of water, so we want to get rid of this moles of methane. So that's how we know it will go on the bottom, because they will cancel out when doing the multiplication. And then on the top will go moles of water. So how do we know what numbers to put? Well, that's where the equation comes into play. So we have 1 mole of methane per 2 moles of water. So 1, 2. And then these moles cancel out. Our answer would be left in moles of water. And we get equals 0.528 moles of H2O. So let's look at a more complicated problem. This one involves an extra step. So we're going to have to go back to our chart a couple times. So if we have 15 grams of aluminum is reacted with excess sulfuric acid, there's that excess again, we don't have to worry about sulfuric acid. How many grams of aluminum sulfate will be produced? So we start with 15 grams of aluminum. Okay, and we want to get to our answer in grams of aluminum sulfate. So let's go to our chart. We're starting in mass of A, we want to go to mass of C. So we have to go to the moles of A, then we go to moles of C, then we go to mass of C. So let's do that. So we have 15 grams of aluminum. What's going to go on the bottom? Grams of aluminum. We're going to want this to cancel out. From grams of aluminum, we can go to moles of aluminum. Okay, and how do we know the values? Well, we have to look at the periodic table. And when you're going from grams to moles, it's very easy. So to find the grams, you just have to look at the molar weight on the periodic table, which for aluminum is 26.982. And then the mole is very easy. When you're going from grams to mole, it's always going to be 1. Okay, and then now we have to set up the next part. So grams of aluminum cancel out. Now we're in moles of aluminum. So we also want that to cancel out because that's not what we want to answer in. But now that we're in moles of aluminum, now we can convert to another substance. Now we can go to moles of aluminum sulfate because our chemical equation tells us that there's a relationship between the two. So if we look at the equation, we see 2 moles of aluminum per 1 mole of aluminum sulfate. There's an imaginary 1 there. So 2, 1. Okay, but we're not done yet. We want to answer in grams of aluminum sulfate. So like it did before, these moles cancel out. Now we're in moles of aluminum sulfate. So that's what's going to go on the bottom again. And then on the top, from now we can go from moles of aluminum sulfate to grams of aluminum sulfate. Okay, so again, like I told before, when you're going from moles to grams, it's always going to be a 1 with the mole. And then now, to find the grams of aluminum sulfate, you're going to have to do a little bit of arithmetic and multiplication. So we have to do 2 times the molar weight of aluminum plus 3 times the molar weight of sulfur plus 12 times the molar weight of oxygen. And if you add that all together, you should get about 342.14. And then now if we do this all together, so we'll multiply the top. So we have 15 times 1 times 1 times 342.14. We get 5,132.1. Then we can multiply the bottom together. 26.982 times 2 times 1. 53.964. And then now we're just going to divide the two. And we should get 95.1 grams of aluminum sulfate. So if we have 15 grams of aluminum and react it with an excess amount of sulfuric acid, this is how much aluminum sulfate will be produced from this amount of aluminum. So the aluminum will run out, there'll still be some sulfuric acid left, and then there'll be this amount of aluminum sulfate. So now let's do a problem that involves formula units. So we have 2 moles of iron oxide react with 3 moles of carbon to create 4 moles of iron and 3 moles of carbon dioxide. And we have this problem. How many molecules of CO2 will be produced from 27 grams of iron oxide reacting with excess carbon? Okay, so we are starting off with 27.0 grams of iron oxide. So we want to go from grams to molecules. So let's go back to our chart. So we're going to go from mass to moles of another substance, now to molecules. Okay, so again, like the other ones, we're going to want to cancel out. Again, we're doing grams to moles to grams, so this is going to be 1. Then we have to do the same thing that we did with aluminum sulfate, with the looking at the periodic table, looking at the individual molar masses, and multiplying / adding them together. And we should get, for iron oxide, 159.69. It doesn't have to be exact, it should be around that number. Okay, so these cancel out. Now we're in moles of iron oxide. Okay, so let's set up our next part. And then we know that a mole goes on the bottom because we want to cancel that moles out. And then on the top, now that we're in moles of iron oxide, now we can switch substances. So now we can go to carbon dioxide because look, there's a relationship between them right here. Okay, so now just to know what numbers we need to put, we just look. So we see 2 moles of iron oxide per 3 moles of carbon dioxide. Okay, so 2, 3. Okay. So now that we're in moles of CO2, now we can go to molecules of CO2. Okay. And again, like when we're doing with grams to moles and moles to grams, when we're doing moles to molecules or molecules to moles, it's always going to be 1 molecule. Or sorry, 1 mole. But what do we put? What number do we put for molecules? Well, do you remember what a mole represents? What amount a mole represents? This number right here, Avogadro's number. That is a mole right there. So if we go back and then we see, we just add this conversion, and that's what we get. So if we add this all together, let's multiply the top. So we get 27 times 1 times 3 times Avogadro's number, which is 6.022 times 10 to the power of 23. So on the top we should get a very large number, 4.88 times 10 to the 25. And then on the bottom, we will get on the bottom we get 159.69 times 2 times 1. We get 319.38. And then if we divide these, we should get, we should get 1.53 times 10 to the 23 molecules of CO2, which molecules will always 99% of the time be a big number because molecules are so small, atoms are so small, that even what we think might be a small amount in mass or in moles will actually be a large amount in molecules, right? So this is why we use a mole to represent amounts in chemistry, because if we just use molecules, it's not efficient because these numbers are so large. But basically that is stoichiometry. It is not the easiest thing in the world, but with a lot of practice, you can get very good at it and then eventually start doing this with different types of values such as molarity and density. Please leave in the comments any subjects you would like us to cover.